Welcome to analyzing quadratic functions for Pre-Calculus Math 11, and we're going to take a look at standard quadratic functions, which is section 4.4. Last class, or in class, we took a look at that math lab where we took a look at constants A, P, and Q, and basically how do they change certain aspects of the standard parabola. And when we look at these graphs, what we should have noticed is a real occurring trend depending on where the number was located. So what I have here is I have a few graphs here. In black here, I'm going to write down the equation of the standard graph, y equals x squared, for both of these. There's y equals x squared as well. Let me go in blue here for the kind of fainter graph. It looks like that's a y equals x squared plus 2. So that's something that's written outside the function, so a q value, and x squared minus 3. So really, what does that q value do? When you see it grouped outside, so this is outside of the square, what it does is it changes the y values, and the q the q values translates the graph. So translates like shift, translates the graph up or down. So when it's located outside of the square, it's changing a y thing. Y things are up, down. And what it does is it shifts it up, down, or translates the graph up or down. When q is positive, so if we have a positive q, it is a shift up. And we have a negative q, it's a shift down. And for our purposes, when we talk about shift up, down, really all we're doing is we're just adding that amount or subtracting that amount from the standard y values. Another way to think of it is, where does the vertex go? The vertex moves to 0, whatever q is. So from that standard point, from that vertex of 0, q, for instance, on the left-hand graph here, 0, 2, we still draw a standard graph. Out 1, up 1 on both sides. 2, 4, 3, 9, etc., etc., etc. So let's take a look at the p-value. What does p-value do? So again, let's write down some of these things here. My graph here is y equals x squared. In black, y equals x squared. Let me go with blue. This is y equals x minus 3 squared. This is y equals x plus 2 squared. So the p-value, where's the p-value located? So the p-value is located inside the square. So stuff that's grouped inside the square, that's probably going to change x stuff. And in this case, the p-value translates the graph left or right. So a shift left, right. Now, a little bit different here because it's written as x minus p. When p is positive, we have a shift. So p is positive, so it's minus p. That is going to be a value of a shift right. And when p is negative, negative p, we get a shift left. So what happens here, as long as it's written as x minus p, we get the vertex of p, 0. And again, we just draw that standard graph. If we combine both the p and q values, what we're going to end up with is a vertex of p, q. So as long as it's written in the form y equals x minus p all squared plus q, our vertex is pq. That's worthwhile remembering, I think. So let's take a look at changing a squared. Last class, you should have seen some sort of change in that first coefficient there. we have a couple of graphs here. We have y equals x squared, and in blue here, this fainter graph, we actually have 2x squared. And over here we have y equals a half x squared, and again in black is our standard y equals x squared. So what does the a value do? A value, again, located outside the square term. So probably a y changing thing. How does it change y? Well, it's multiplication. Multiplication causes some sort of expansion compression. So the a value expands or compresses the y values. So what do? We actually take whatever y values we're supposed to have and we just multiply it by a. So what happens is if a is bigger than 1, we have expand. And if a is in between 1 and 0, we have compress. Perfect. So let's go to what happens when a is negative. Here we have the effect of changing the sign of a. So my two graphs here are y equals x squared, and again in blue, y equals negative x squared in this case. Again, the a value is outside. When it's negative, what that's going to do is change some sort of y value thing. And if the a value is negative, the parabola opens down. Now really, why does it open down? Is because we're taking whatever our corresponding or whatever our y values are, and we're multiplying now by a negative sign. So if it was positive, it gets flipped across and it becomes a negative. So each of these things separately can be used to graph an equation. So there's a standard quadratic equation. There's certain things going on. I like diagramming what's going on. But first, just for our interest's sake, let me in kind of a lighter gray here. Let me draw down a, let's go in black. What y equals x squared, well, hold on. Let's graph, or pick off some information. So we have a vertex of 4 and 2. So the 4 and the 2 creates our vertex. We have an a value of 1/3, so that's us compressing by 1/3. And we have a negative sign. So that opens down. So for these parabolas, what I want to do is let's move to the vertex 4. In this case, the vertex is at 4, 2. So 1, 2, 3, 4, 2. There's a vertex of 4, 2, assuming that each of those are one unit. Typically, we go out 1, up 1, but because it's opening down, we go out 1, down 1. Except, now we multiply that y value by 1/3. So instead of 1, 1, it's 1, 1/3. 2, 4. 4 divided by 3 is 4/3, which is 1 1/3. 3, 9, that's a good one. 3, 9, when we divide 9 by 3, that's 3, so it should be 3, 3. That's perfect. What other factors of 9? Because those are usually the ones that are really good. I've kind of made it a little bit bigger dots because those really fall nicely on hash marks. 4 squared is 16, so that divided by 3 isn't that great. 5 squared is 25, that's also not that great. 6 squared is 36, so that divides nicely by 3, so let's see if that will fit. 6, out 6, 1, 2, 3, 4, 5, 6. And I said 36 divided by 3, or 1/3 times 36 is 12. 1, 2, 3, 4, 5. So that point does fit kind of nicely on our graph. Let me draw that one in there on the other side, again because of symmetry, and we can connect these dots. Now really, drawing as many dots as I did might not be as important. Kind of missed one on the left hand side there, but it might not be as important as getting at least some of the closer ones. So what we notice is it's opening down. Did we take care of that? Yep. Is it compressed by a third? It is. And is the vertex at 4,2? It sure is. We should be able to do it going the other way as well. Same kind of idea. We're just going to pick off information given a graph. We want to find out where the vertex is. That should be fairly straightforward to pick off. It looks like it's at -3, -6. What that tells us is that we can write an equation, y equals, I don't know a quite yet, but certainly the x minus -3 and the q value of -6. And how are we going to deal with this is we can take any point that's on the curve. Because the point is on the curve, if we know an xy coordinate, we can plug that in and find a. So, I don't know, let's try the point. Let us use, well, looks like -1, 2 is a fairly straightforward point. So let's plug in 2 for y, -1 plus 3 squared minus 6. -1 plus 3 is +2 squared minus 6. Let's extend this up here. We can add 6 to the other side to make it 8 equals 4a, and dividing by 4 we get a equals 2. So we get a final answer here of the a value is 2. It's definitely opening up, so it has to be positive. The x minus the p value was -3x minus -3 makes it +3, we've seen, all squared, and minus 6. So all of this should really be kind of a lot of review, not so much of how to graph them specifically, but we did do a huge lab on this stuff. That ends the notes for analyzing quadratic functions for standard quadratic functions section 4.4.